Hello, everyone. Welcome to the Atto Fridays. Our speaker this week is Dr. Vasileios Balos. And when he's not chasing his daughter around or cheering on his team,
Uh,
Panathinaikos.
that's it.
Yes,
You got it.
yes. Dr. Vasileios Balos somehow finds a little time for science, and after earning his BSc and MSci in applied physics from the National Technical University of Athens, he completed a PhD in physical chemistry at the Max Planck Institute for Polymer Research in Mainz through the University of Amsterdam in 2017, and then he spent 4 years as a postdoc at the Fritz Haber Institute in Berlin before receiving a Marie Curie Individual Fellowship in 2021, which brought him to IMDEA Nanoscience in Madrid. And since 2024, he leads his own independent research group there, studying molecular level liquid dynamics with advanced nonlinear bulk and surface sensitive spectroscopy. And he's proving somehow that science still finds a little time between daughter snuggles and football, basketball, and volleyball matches. You always find time for science, right?
I watch everything. Yes, I do. I mean, it's one of my hobbies, let's say. I mean, being the personal life being the main job, I mean, my hobby is science. So I need to disconnect a bit. So,
All
should I
right,
start?
start, yeah.
Yeah,
So
thank you very
welcome
much.
to the Atto Fridays. You talk about hydrogen bonds and energy flow, insights from terahertz nonlinear spectroscopy. We're ready.
So, thank you very much, Carla, for the kind introduction and all the people that are connected here to watch this talk. I mean, first of all, I would like to say that from the title of this seminar, I mean, talking about Atto Fridays, I mean, I feel kind of an intruder, let's say, because I mean, you will realize from the talk that I mean, I'm not doing Atto. I'm doing ultra fast, and usually I am the fastest guy, let's say, in my community. But in your case, I'm a bit slow. So what I will ask you to do is slow a bit down your detectors, let's say, and try to follow this presentation because my molecules are moving slower than what you are used to. So I am Vasileios Balos. I'm a project leader now at IMDEA of the group of bulk and surface nonlinear liquid dynamics. And my talk today, as you can see, is from hydrogen bonds to energy flow, insights from terahertz nonlinear spectroscopy. And already from the talk, there are some hints that I would like to stress out. First of all, I'm going to talk about hydrogen bonds. So that basically brings you in mind, I mean, hydrogen bonded liquids, the most famous and, let's say, famous one being water. And of course, I will speak for a lot of liquids, but in our case, water will be the central topic. I will talk about the energy flow inside the liquid, inside the intermolecular motions of the liquid and dynamics, how this energy flows, and this is very important. And all this will be done from a perspective of nonlinear terahertz spectroscopy. So just to give you a small heads up of what will follow, I mean, I will try to introduce and motivate this talk talking about terahertz spectroscopy, hydrogen bonds, and energy transfer, and how these are important. Then I will introduce you to nonlinear terahertz spectroscopy, and most importantly, the Terahertz Kerr Effect experiment, which is the main working horse from the terahertz part of my job here at IMDEA. Then, I mean, I will be talking for how we implement this Terahertz Kerr Effect spectroscopy to identify, let's say, the low frequency dynamics of water and what it happens when we put ions inside. And then I will do a small detour and talk to you about the fundamentals, let's say, of Terahertz Kerr Effect spectroscopy once I have shown you how important this is, and to talk to you about the effect of the electric, basically, and the magnetic field of these high power terahertz pulses. So, starting terahertz spectroscopy, liquid water, and energy flow. Let's see now. Why terahertz spectroscopy? I mean, what is important about the terahertz spectroscopy? What is terahertz spectroscopy? So the terahertz radiation, let's say, stands where you see it. I mean, in the electromagnetic spectrum. I mean, it's in Spanish, but it's more or less, I mean, universal. the language. I mean, it's Latin. So the terahertz radiation is found between microwaves and infrared. And this part of the electromagnetic radiation in general, it has been, I mean, up to recently, it was characterized as the terahertz gap. And the reason is that it was very difficult to cover this region of the electromagnetic spectrum. And the reason for this difficulty was that, on the one hand, as you can see, terahertz radiation is faster than common electronics that we use for microwaves. But on the other hand, is slow for infrared radiation, where you use electronic transitions. I mean, with the advancement of ultrafast lasers, I mean, ultrafast amplified systems, and we managed to get routinely terahertz pulses in benchtop sources. And roughly 25 years ago, and then the whole progress started. I mean, making new detectors and new terahertz generators, new ways of generating terahertz with different characteristics, and so on and so forth. So why terahertz? I mean, why it is important? I mean, actually, the terahertz radiation, I mean, has resonances, has these characteristics. So a pulse duration of around 1 picosecond, a wavelength around 300 microns, and a photon energy of 4 electron volt. And this is very important for all the states of matter. I mean, for example, it is in resonance with molecular alignment and anti-alignment in gases that have molecules or atoms with a permanent dipole, molecules basically with a permanent dipole moment. For liquids, which is the main topic of this talk, it's very important because it's directly talking and interrogating the intermolecular motions of these liquids. And in solids, it is in resonance with phonon modes, and also it can interrogate charge transfer in semiconductors and conductors. And as I told you before, here we are focusing in the intermolecular motions of liquids. Just to give you a bit more of an idea, this is how a terahertz setup looks like. I mean, this is the simplest case of what we call terahertz TDS. I mean, it is the counterpart, let's say, of IR spectroscopy, but with a twist. And what is the twist? I mean, you can see that basically what we do is that we split the pulse coming from our laser. I mean, it can be, usually it's an 800 nanometer pulse. We pre-split it. I mean, in that case, it was 1500, but the way of thought is the same. You use the main part of the light in order to excite your terahertz crystal, which in that case is this DAST crystal. You generate your terahertz pulses, and then with parabolic mirrors, you focus them to your sample, you collimate them, and in the end of the day, you focus them to this crystal here, gallium phosphide in that case, which is your detection crystal. I mean, this is important because the detection crystal, basically, it's a crystal that is inherently, let's say, birefringent. And what happens is that by focusing the terahertz, you are creating a birefringence on top. So a transient birefringence that basically has a duration dictated by your terahertz pulse. And then this transiently induced birefringence is being read by the rest of the radiation that we split it in the beginning. It comes linearly polarized, then it passes through the area that you have excited, reads the birefringence, acquires ellipticity, and this ellipticity via a lambda quarter plate and a Wollaston prism is being splitted in, is being read in a difference detector, let's say in difference photodiode, which actually is a replica, an exact replica in the time domain of our terahertz signal. And the importance of this thing, I mean, this is very important because, I mean, this is the twist that I told you before. I mean, you are not doing a detection with a common detector, which gives you only the intensity spectrum. I mean, it has the potential to give you basically the full, let's say, amplitude and phase of your terahertz pulse. And this is very important because it gives you access not only to the real, but to the imaginary part of quantities like the refractive index, the permittivity, so you get the complex permittivity, and in the end of the day, the complex conductivity, because all these are interconnected. So now that I hope I convinced you that terahertz has great potential, I mean, even in its simplest case, let's move on and talk about water. So water from your chemistry lectures, I don't know, I mean, even from primary school, you don't even need to go to chemistry lectures. It's been characterized as a liquid of life, and this is true. It's omnipresent, it's everywhere. And it is this H2O molecule. I mean, very important for environmental processes, very important for biological processes, very important in technological processes. I mean, it's everywhere basically. But here there is, I mean, this image is a bit deceptive, let's say, because the water molecule, I mean, it's not exactly H2O. What it happens is that it belongs to a network formed by water molecules connected with other neighbors via hydrogen bonds. This exotic, let's say, kind of chemical bonds. And this gives to water many of its peculiarities, let's say. Water basically has more than 70 anomalies. Let's say anomalies from the point of view that it doesn't behave as one would expect it to behave, and this is what makes it so important. So the single water molecule, let's say, representation cannot explain almost any of this liquid's behavior, and the abilities are attributed to the complex H-bonded network. It constitutes this network by thermally fluctuating hydrogen bonds, and it's in an almost tetrahedral configuration. So usually you have a central water molecule bound with four, creating, let's say, hydrogen bonds with, on average, four other water molecules in its pure state. And I mean, the good thing for us, the fortunate thing for us that are doing terahertz spectroscopy is that the lifetime of the breaking and reformation of these hydrogen bonds lies to the limit, let's say, of 1 picosecond, which brings us basically to gigahertz to terahertz frequencies. If you see now the low frequency spectrum of water, I mean, where you have all the intermolecular motions, so motions between, I mean, the communication between the water molecules, you will see that it is very, very, very complex and broad in its dynamics. You have this T1 that lies around 20 gigahertz, which is considered to be the cluster of water molecules reorientation. Then you have this tau 2, which is basically the single molecule reorientation, even though, I mean, this is still under debate. But anyways, the trend now is to call it the single molecule reorientation. So a single water molecule, because of its dipole moment, coupling to the terahertz field and feeling the torque and responding. And then if you move on to higher frequency, you find quicker and quicker intermolecular motions like the OH vibration at around 4 to 5 terahertz, or a bit higher, basically. And then, last but not least, the librations, which lie around 12.5 terahertz. So, I mean, you can see, at the end of the day, what you have to remember is that these dynamics are very complex, they are overlapping, and because of this overlap that is happening there, energetically, it gives pathways for excess heat deposition. And why is this important? Well, the energy transfer in liquids, and especially in water, is very important because, for example, I mean, it's very important for the climate control and regulations, because as water acts like a heat reservoir due to its high heat capacity, it's used as a thermal buffer for biochemical reactions, and it's cooling down essentially every machine that we have, I mean, from chillers in our labs, cars, and whatever, and so on and so forth. So, now, I mean, I finished the part of, I mean, explaining what is the terahertz spectroscopy in general, and I come to the other part that, I mean, lately, I mean, with the advance of the terahertz spectroscopy, we are reaching in higher and higher and higher field strengths. And we are reaching to the point that we have so high field strengths that we can basically induce non-linearities even to hydrogen bonded materials, let's say like liquid water, which is something very difficult to achieve. I mean, you can see these recent publications. This is the Terahertz effect. I mean, this one we will see it, we will encounter it many times in this talk. This is the Terahertz Kerr Effect time trace of liquid water coming from my former group in the Fritz Haber Institute in Berlin. Then there is Martina Havenith in Bochum, where she uses terahertz radiation, high field terahertz radiation, pumping basically at the librational mode, so around 12.3 terahertz. Or even we have today, I mean, 2D approaches like the 2D Raman terahertz, which was first reported by Peter Ham in the ATH in Zurich. So, I mean, this is a field which is currently increasing, and it's, I mean, it's becoming more and more important. And let's see what we can learn when we are using these high field terahertz pulses into the H-bonded system of liquid water. So, as I told you before, the working horse is what is called the nonlinear terahertz spectroscopy, Terahertz Kerr Effect spectroscopy, so the TK. Basically, I don't know for how many of you are familiar with the optical Kerr effect, which is, let's say, the optical counterpart of this terahertz Kerr effect. But basically, the optical Kerr effect, what you are doing is that you are using an optical excitation, you are inducing a birefringence in your sample. I mean, if you remember before, in order to do this electro-optic sampling, what we were doing is that we were putting a birefringent crystal, focusing the terahertz and increasing its birefringence and then measuring it. Now, you have to imagine this experiment as instead of having this detection crystal, you directly have your sample. And the induced birefringence from the terahertz pulse or the optical pulse and the optical Kerr effect goes directly into your sample, and this is what your probe pulse is measuring. I mean, here in our case, we have a lithium niobate source, which the spectrum of which is this. I mean, it peaks at around 1 terahertz, and we use this in order to see the low frequency dynamics of water. In order to understand now microscopically what will happen, I mean, imagine a permanent dipole, like a water molecule, which is, let's say, aligned or, I mean, with an angle theta. Now you have your terahertz pulse, which introduces a torque. I mean, basically, it communicates, it talks to this permanent dipole moment with its electric field and aligns it, I mean, to a certain direction. And this is what induces birefringence. And then the optical probe pulse, whose polarization is rotated at 45 degrees, transverses this sample and reads this induced birefringence. So this induced birefringence basically is basically the most important quantity, the measurable, let's say, that we have in such an experiment, and it's proportional basically to this assembled average of cosine squared theta minus 1/3, which is basically directly connected with molecular alignment. So using this experiment, what we want to do is to drive nonpolar and polar liquids with terahertz waves and monitor these dynamics of the optical birefringence. Now let's see, I mean, this is DMSO. Let's see how a usual, let's say, Terahertz Kerr effect time trace looks like. I mean, basically what you have here is at time zero, you have an electronic response. I mean, electrons are faster than the nucleus, so they are the first that respond to the interaction with the terahertz field. And then this is followed by a nuclear relaxation, which corresponds to the molecular alignment. I mean, this relaxation is usually exponential, but not always mono-exponential. It can be bi-exponential, or depending on your system, have more exponential, let's say, decays appearing. As I told you before, the molecular alignment, we know that it's proportional to the susceptibility of the orientation plus 2 times or multiplied by 2 times the interaction with the electric field. I mean, if you remember a terahertz pulse, basically it has 2 lobes. So one interaction with the first lobe and another interaction with the second lobe, and all this multiplied by a response function. And the total interaction, in order to figure out what our total interaction will be, we have to include also the probe pulse. So you have to multiply all this with the probe pulse itself and this delta alpha, which is the polarizability anisotropy. So the important notions that you have to get from such an experiment is that, first of all, it is an inverse Raman process. So basically, if you Fourier transform your response, you will get the low frequency Raman, let's say, spectrum of your sample. And as a Raman process, of course, only active Raman processes will respond, so connected with the polarizability of the molecules, and that the main observable that we have here and dictates the sign is this polarizability anisotropy. Now let's see what's happening with water. I mean, in order to find out what's happening in water, I mean, this is not a chronological thing. I mean, first of all, of course, we went to the liquid water, but I mean, what we did here is that we came with a top, let's say, illumination at a bucket of water where we had control of the temperature. Initially, we started with a high temperature where you have a lot of vapor on top of your liquid. And I mean, what we observed by the Terahertz Kerr effect is basically that this water vapor gives us the typical thing that you expect from a vapor. You have, again, this electronic rise, and then this is followed by oscillation marking basically aligned and anti-aligned states. But as we started to drop down the temperature and to condense the liquid, to go to more and more liquid phase, you can see that something weird was happening. So this signal from these oscillations, it started becoming more and more bipolar to end up in a room at a room temperature with this black, let's say, line. And as you can see, the first thing that everybody notices is that this signal is bipolar and is in contrast to what I showed you before for DMSO. And I can tell you now that we measured more than 30 liquids, and I mean, no one had this very pronounced bipolarity that came from the liquid water. So knowing that, we directly realized that one of, let's say, holy grails for us was to understand why this bipolarity, what does it want to tell us? What does it tell us? The first thing we did is like, okay, I mean, I have this bipolarity. Here you have, by the way, the optical Kerr effect response of water, where you can see that, I mean, everything is positive. But when you go to the Terahertz counterpart, Terahertz Kerr effect, you can see that we have this bipolarity. So the question is now, why bipolar? So we know that I showed you before the response function, and checking one by one the quantities, one would realize that the only thing that can give a negative sign, let's say, to this induced to this Terahertz Kerr effect signal, it's this polarizability and isotropy of water. So we said, okay, most probably we found it. Let's check the literature and let's see what people have calculated for the polarizability and isotropy of water. But everywhere we looked, we saw that this polarizability and isotropy, it was reported. I mean, they had different values depending on the publication and the simulation types and force fields that they were using, but it was always positive. So that means that the polarizability and isotropy itself cannot explain this bipolarity. So there, I mean, since we are experimentalists, we are, I mean, more limited people than let's say, people from simulation. So we went to our simulators, to our theory guys, counterparts, and we asked them to simulate the whole experiment. And what they did is that they performed ab initio simulations with 128 water molecules in the box, and classical MD simulations, so force field simulations. And what they saw is I mean, the response they simulated for us, the cosine theta, which is the orientation, a cosine square theta, which, as I told you before, is connected with the alignment. And what they found out is this response. So, I mean, there were two problems with what they calculated. First of all, the alignment overestimates the birefringence by 2 orders of magnitude, so it was not realistic. And another thing that they saw is that there was no relaxation tail there. So no relaxation tail means that if this was real, I mean, the Terahertz pulse will interact with the water molecule, and the water molecules, instead of rotating or whatever, they will just jiggle. So from there, we couldn't get an answer. But then, I mean, we had the idea to tell them that since you have the boxes and the simulations and so on, please calculate us the energy, the energetics, let's say, between rotations and translations. And there, both from AMD and force field molecular dynamic simulations, we saw something very surprising. I mean, basically what was happening is that after the interaction with the terahertz field, what was happening is that we were seeing an increase in the translational degrees of freedom. And this is an indication, basically, that what we do with our terahertz pulse is that we indeed talk to the rotations, but then you have an ultrafast, let's say, water, it's here in this diagram, you have an ultrafast dissipation of energy in the translational degrees of freedom. So then, since we had this indication, we said, okay, let's check now which of the translational modes that I told you before can appear. I mean, don't forget that this mode should be Raman active. And one Raman active mode that does not appear let's say, clearly bipolar spectra like FTIR is this water bending mode, which is right above 1 terahertz. It's neighboring to the single molecular reorientation. And the important thing there is that, I mean, the breadth of this was giving us exactly the time of this exponential decay from the water molecule. So what we suggested there is that basically what is happening is that the terahertz pulse interacts with the water molecules, but in our case, and contrary to our initial beliefs, it's not interacting. I mean, the polarizability and isotropy is not the polarizability and isotropy of a single water molecule, but better is the polarizability and isotropy of a cluster. So it involves at least 2 or more water molecules. And then we get our response. Okay, so then we pass to the case of ions. So why is this important? Because initially in my presentation, I kind of lied to you. I told you that water is the liquid of life, but it is not. Actually, water is a poison. Pure water is poison. If you drink a lot of pure water, I mean, at some point you will dilute so much the electrolytes in your system that you will die. So, what makes water, being the liquid of life, it's actually the impurities inside the water. And the most common impurities inside water are inorganic salts, which they can interact with solute inside the body or the cell or whatever, or they can interact also with the water itself, altering its H-bonded network. So traditionally, ions are being, ions are being split in two categories. This is the traditional, way of seeing them. You have the cosmotropes or structure makers, which are usually anions and cations that have a high surface charge density, and the chaotropes, the ones that, from the word chaos, basically, where basically you destroy the water structure, let's say this tetrahedral perfect structure, and they are usually, traditionally again, connected with a low surface charge. But this model, it has been rendered lately as oversimplified because, on the one hand, it doesn't take into account the sign of the ion, which should be important because sign of the ion dictates the hydration mechanism or how the water is distributed around these ions. And then it does not, it cannot explain the temperature and pH dependence of liquid water. So, in this series of ions, you can see, usually sodium and chloride, they are considered to be somewhere in the between. And this is why always we use them, where we could, because of dilution, you are using them as the counter ion in order to have, let's say, a neutral effect from the counter ion. So basically, we did the same experiment with several concentration of chaotropes, strong cations and strong anions. So strong meaning highly charged. For cations, it was we started from potassium, sodium, lithium, and magnesium, which is the most highly charged. And what we saw at the same concentrations, we saw basically that we always had the trend that our TK signal was increasing in amplitude. On the other hand, very surprisingly, we saw that for anions, quite the opposite was happening. So by introducing anions that are considered to be cosmotropes, this energy transfer was disrupted. And in both cases, the time constant was seen unaffected. So this was a very curious, let's say, indication that forced us again to see what is happening. Then we did some temperature, some concentration dependence for every salt, and we saw basically that we had an almost perfect, let's say, linear trend for all the ions. And checking what is happening with the highest concentration of ions and the signal, the TK signal, we saw that apart from fluoride, which is, let's say, the villain in this case, we saw, that there was a direct connection to the surface charge density as traditionally, let's say, suggested. But, for strong cations, it was increasing. For strong anions, it was decreasing. And I remind you again that increasing signal in our language means increasing energy transfer or decreasing, disrupted energy transfer. So again, we went to our theory counterparts and we told them, okay, please simulate this for us. And they did it for, on the top floor, you can see for magnesium and sodium sulfate. You can see that they did, for magnesium, they did several, let's say, concentrations. For sulfate, for sodium sulfate, they did only one concentration. For magnesium, they captured perfectly the trend. So, this increase in the signal. For sodium sulfate, we had a semi-agreement, let's say. But in any case, they didn't see any increase in the signal. If any, they saw some reduction. And then we asked them to split the contributions in single molecule, which is the blue one, and collision induced, which is the green one. And as you can see, anions and cations have a completely opposite behavior. So then another thing that we asked them to do is to check and see the energy transfer itself. And as you see, again, we have a semi-agreement for cations. For magnesium, in all the concentrations, we can see that this energy transfer between reorientational and translational modes is increasing, while for sodium sulfate, we saw an increase, but it was a very, very moderate increase, that at no case justifies, let's say, the reduction of the signal that we are seeing. And also, we asked them since they already had the box and everything was ready, we asked them to calculate the average H bond strength for the around a cation and an ion, between a cation and an ion, and for bulk water. And as you can see from the two first bars, let's say for magnesium chloride and sodium sulfate, you can see that we have a clear disruption of the hydrogen bond network for highly charged anions. So basically, what this means in simple words, I mean that the initially, let's say, traditional way of thinking of cosmotropes and chaootropes between anions and cations is essentially wrong, because at least for the highly charged species of anions and cations, because cations, what they are doing is that they are structuring water around them, and basically that favors the energy transfer between the modes, while anions have the opposite effect. For the anions, basically, they are by participating themselves in the hydrogen bonded network of liquid water, because an anion can basically replace a water molecule, they essentially disrupt this energy flow. So we spoke about highly charged anions and cations, and let's see now, I mean, the question that comes is like, what's happening when we have lowly charged anions and cations? So for lowly charged anions and cations, we did exactly the same. We used series of potassium fluoride, potassium chloride, potassium bromide, and iodide. I mean, this is a decreasing, let's say, surface charge density from fluoride to iodide. And we saw, contrary to their highly charged counterparts, that they are increasing, actually, at least the Terahertz Kerr Effect signal. So the polarizability anisotropy, this is where we can comment, is increased. And it increases linearly with the polarizability, because for the anions, I mean, an ion that it's lowly charged and an ion that's lowly charged has a polarizability. And basically, as I told you before, it participates to the hydrogen bonded network of water. So this increase, I mean, it's not justified by as with the highly charged cations before. So what we did is that we plotted everything against the polarizability, the gas phase polarizability, and we see just a linear increase. Going now to the cations, to lowly charged cations, we saw actually again the same effect. Basically, the cations, no matter the nature, I mean the lowly charged cations, they were increasing the TK signal, so the polarizability anisotropy. And basically, what this, I mean, by doing the same, let's say, exercise as before, finding and calculating their polarizability and using it as the x-axis, you can see that we have a perfect linear trend. So both for cations and anions, we have a perfect linear trend, which is fine. But you have to see here to pay attention to the scales of the y-axis. You can see that for cations, we have the increase, let's say, in our Terahertz Kerr Effect signal is much more drastic. And the question is why this is happening. So what we came out from what our simulations indicate to us is that the whole difference, I mean, the whole reason why we see this increase for lowly charged cations and the increase for lowly charged anions comes from the way they are hydrated, basically. So cations do not participate in the hydrogen bonded network of water. So what is happening is our Terahertz false induces this, I mean, talks to the reorientational degrees of freedom. I mean, it creates this bending mode, so this restricted translation. And basically what is happening is that you have a billiard, let's say, effect. So the water molecule hits the neighboring cation and basically have this collision-induced polarizability. While on the other hand, for anions, the story is different. They participate in the hydrogen bonding network of water, so it's the polarizability itself of themselves that is creating this excess in our Terahertz Kerr Effect signal. So basically, for summary in the electrolyte solutions, I hope you got convinced that we can resolve the ultrafast energy transfer from reorientational to translational intermolecular degrees of freedom. The cations and anions, according to the surface charge density and polarity, they affect distantly the energy landscape of liquid water. The cations, independently of the surface charge density, increase the TKE amplitude and the energy transfer, but with different reasoning. So highly charged cations by strengthening the H-bond system, lowly charged cations by collision-induced energy transfer, so like a billiard effect. While for anions, we have two distinct behaviors depending on their surface charge density. If they are highly charged, they disrupt the energy transfer, while where they are lowly charged, I mean, basically they increase the TKE amplitude by contributing with their polarizability. So then I'm going quickly, since we finished this part. I hope I showed you, I mean, the importance and how instructive Terahertz Kerr Effect spectroscopy and nonlinear Terahertz spectroscopy can be, at least for studying molecular liquids. But as I told you before, this field is in its infancy. So one of the things that we wanted to do is to go to the fundamentals. And basically, we wanted to see what is happening, I mean, in molecular terms, I mean, at the time of the interaction. So what is happening when a molecule it interacts with this high terahertz electric field. As you can notice, I mean, the terahertz electric field that you see here has two lobes. The peak intensities of whose are separated by 0.5 picoseconds. I mean, the electric field is also accompanied by a terahertz magnetic field. So here the task is to see what is the effect of the terahertz electric field and then the magnetic field. I will go on very quickly here. So, as I told you before, you have seen this equation many times. I mean, the alignment induced by an experiment is the ensemble average of the cos square theta minus 1/3. And this quantity has been shown to be proportional basically to the susceptibility of the liquid. So we did this very simple, let's say, modeling. I mean, this even as experimentalists, we managed to do it. It's a very small modeling. So we consider a liquid which has one Debye process. And we managed to get the permittivity, I mean, real and imaginary part of the dielectric permittivity. And then we tried to simulate, let's say, to see how the cosine theta will react. I mean, this is the responses that we got. And as you can see here, I mean, there is a peculiarity already. And the peculiarity is that by increasing the polarity of the liquid, the first half cycle of the terahertz pulse, I mean, gains almost 1.5 times higher amplitude than the second half cycle. And the only plausible explanation to such an effect would be that the second half cycle should find a liquid which is already partially aligned from the first half cycle. This is a very important observation, and I will explain you later why. So first of all, we need to confirm that what we see is true. So, I mean, what you showed before was the cosine theta, but as I told you before, which shows the orientation, but here the important quantity is the cosine square theta. So what we did is that we took this model molecule and we tried to calculate the cosine square theta and observe how this is changing by changing the polarity of the liquid. And as you can see, we continue to see exactly the same response. And that, in simple words, would mean that basically what is happening is that at time zero, I mean, before the terahertz pulse comes into play, you have the molecule in its native state, and the electric field starts to act, building up for finding the first lobe. So when it finds the first field, I mean, it aligns the molecules, then it drops again with crossing the zero, it drops again to its native state, then crossing the second lobe, it partially anti-aligns, then it partially aligns again, reaching basically to its end state. I mean, this is very important because if this is true, it would have been the first time that anti-alignment and alignment states have been found for molecular liquids. It has never been reported before. So to support our observations or let's say our, I mean, train of thoughts with real experiments, we chose three liquids. So we chose chloroform as a weakly polar liquid, acetone as an intermediate polarity liquid, and then acetonitrile as a strongly polar liquid, and we performed the TKE experiment. So what we saw is exactly what our model was saying. I mean, for chloroform, you see that we have a stronger interaction, then followed by acetone, and followed by the chloroform. So acetonitrile, sorry, then acetone, and then chloroform. Exactly how it was predicted from our cosine theta. And now, I mean, since we can basically model something with a relaxation tail, that means we can deconvolute the relaxation tail and find actually exactly a perfect agreement with the predictions we made. So another thing that we wanted to do is to see how the nature of the terahertz field, let's say, changes the picture. And this is why we're excited with several sources, I mean, from low frequencies to higher frequencies, and so on and so forth. And what we saw is that basically our prediction is fulfilled to its maximum. And it's 100% roughly, let's say, predictable. For the best agreement, let's say, it's achieved when using low frequency terahertz sources, something that is expected due to the fact that as we reach to higher frequencies, you have more dynamics involved. I mean, I remind you, this very complex spectrum, low frequency spectrum of liquid water. I mean, this is a work in progress, so we are trying to convince our theories. I mean, we have already convinced them. So we hope that this, and we have very, very, let's say, good indications. So we hope that this will be published. Let's say this work will be published soon. And for the last part, that I will go fast, I mean, I promised you that I will show you the terahertz magnetic field. So when you are having a pulse with an enormous, in terahertz terms, electric field, this is always accompanied by a terahertz magnetic field, which reaches at 0.7 Tesla, roughly, and that, I mean, many people, let's say, sometimes forget. So basically, we needed to see what we can do with this terahertz magnetic field, and I mean the experiment that we thought about was to see if we could induce with this terahertz field Faraday rotation in liquids. I mean, this would have been the first time that something like this is reported. So we use the top illumination geometry, and in that case, as you can see, the terahertz magnetic field or the pulse interacts with the liquid, and you have the the probe pulse, let's say, the optical pulse coming with an angle of 40 degrees, a physical angle of 40 degrees. So we did this to several liquids. I mean, as you can see here, I mean, several types of liquids: hexanol, pentanol, butanol, dioxane, THF, chloroform, I mean, whatever you can imagine. And we saw that indeed we had, let's say, indications from Faraday rotation. I mean, if you see there, the response of the rotation is much higher than the electric field. That means that we are able to induce Faraday rotation in liquids, which, if true, I mean, this is a very strong indication, but still, we were not sure. We had to explain that. But if true, it would have been the first time that something like this is reported. And it's very important because Faraday rotation is being used in tons of optoelectronic devices, countless optoelectronic devices, with limitations. So, inducing ultrafast Faraday rotation in liquid species, it would have been something very, very important. So in order to elucidate, let's say, the nature of this light matter interaction causing this rotation, we referred to the classical Kerr effect. So in the description of this effect, the Lorentz force bends the electric current out of plane. So the polarization should basically bend. And in our molecular counterpart, we found out that basically the role of this molecular current can be taken by this first equation. So this GE. Then, I mean, the whole current would be the interaction of this molecular current with the terahertz magnetic field, multiplied by the gamma. So let's say the angle of which of the interaction between the optical and the terahertz pulse. So in that case, the source of the electromagnetic radiation would be the molecular current plus the whole current, and the rotation angle should scale with the effective length multiplied by the polarizability squared. And in order to see whether this is true, we plotted the polarizability of all these liquids that we had, the polarizability squared, with the rotation, the Faraday rotation that we have measured. And you can see that apart from dioxane, we have a perfect match, a perfect linear trend with the square of the polarizability. So this proportionality is confirmed. And another thing that is very striking here is that if you compare it with traditional materials, with huge Faraday rotation like this terbium, gallium, garnet that are being used to optoelectronic devices, you can see that in some cases we can have even further, let's say, higher Faraday rotation than these traditional materials. So, in summary, in the Terahertz effective field, electric field interaction, we see two lobes that produce aligned and anti-aligned states. And this manipulation of alignment states, basically, it can play a huge role in the future of doing coherent control of chemical reactions. This is what we envision. While on the other hand, for the Terahertz magnetic field, we saw that the ultrafast, we proved that there is ultrafast Faraday rotation in liquids. We demonstrated that this is because of the molecular Hall effect. And this gives us a possibility of facile, versatile, and robust devices in the future because a solid can get destroyed, but a liquid cannot get destroyed. So this was all. By closing, I would like to thank very much. I mean, first of all, the group of ultrafast science at IMDEA Nanoscience. I mean, everybody of these people have helped with fruitful discussions and so on and so forth. The people at the Fritz Haber Institute of the Max Planck Society, which basically introduced this whole project and helped a lot, like Professor Martin Wolf, Tobias Kamfrath, Mohsen Sajali, and Gennaro Birchans. External collaborators, I mean, basically the people that are simulating for us, like Professor Roland Netz, Professor Doe Bonwis, Thomas Kuhne, and José Megalbarti, and of course, people that have funded the project, which has taken some years. So that means that we have a lot of funding agencies there. And you for your attention.
Thank you so much for your talk.
Yeah.
It's really
Thank you.
interesting. Other questions, comments? I know it's Friday and people are tired, but it's always time to ask something. We're going to start on Zoom and then we're going to move to our subscribers on YouTube for the questions. So people are quiet today, but do raise your hand or
I may have confused them a lot.
come on, no. I mean, while we wait, I have one question, namely,
Okay.
you mentioned that it's very difficult to align and anti-align molecules in this regime. Why? We have a raised hand.
Because I mean, basically, especially when you are talking about molecules that are, especially for hydrogen bonded liquids, I mean, you have interaction. So it's like you are having, I mean, you are trying to rotate a molecule, but then from the bonding, you have restrictions. And to break these restrictions and to keep an alignment state, I mean, it's basically not impossible because we saw that can happen, but it's you need very specific things, and you need this huge coupling that you have between let's say the reorientational degrees of freedom with the terahertz pulse, so this dipolar motion, and to be able to have really strong terahertz fields in order to align them.
Okay, we have here someone who would like to talk.
This is Bogdan. I know Bogdan.
Go ahead, Bogdan.
Hi, Vasileios. Can you hear
Hi,
me?
Bogdan. Yeah, I can hear you. How is it going?
Great to hear your news and great talk.
Thanks a lot.
Yeah, a quick question. So
Yep.
in the first part on the electrolytes, so your
Yep.
main observables is actually the amplitude of the negative part of the response and
Yes.
the
Basically, I will let you know. Maybe I didn't explain this very well. I mean, basically, when you have, at least in the case of water, what you are having is this bipolarity, no? So you have initially the electronic response, as I told you before, and then basically you have, in order to describe the whole behavior, you need two exponentials. You have a fast exponential decay, which it's very fast for us. Maybe an Atto person can catch it, but it's pretty fast. But then we are focusing on the amplitude of this exponential that brings things back to its native state. So when I'm talking about amplitude, I'm talking about the amplitude of this exponential, which is basically more or less like talking about the negative part.
Yeah, but I was wondering if you can have any additional information from this first part, like the zero crossing time or something like that, if it's informative in any way, or
I mean, for sure, it is informative. I mean, of course, we cannot. I mean, there is no way of us. I mean, we are not fast enough to catch the electronic response. Basically, this is a job for Atto scientists. But also, I mean, with our capabilities, I mean, there are terahertz sources nowadays that can give. I mean, like the spintronic terahertz emitter, for example. This is a new way of creating terahertz pulses, and these are ultra broadband. And ultra broadband pulses means that they are short enough in order to be able to interrogate, let's say, such fast dynamics. With lithium niobate in our case, it is impossible, Bogdan.
okay, thanks a lot. Cheers.
Thank you.
We have another question from Erwan Gillam. Can you please explain again the link between Faraday orientation and molecular Hall effect?
Yeah. So basically, the Faraday rotation is the thing that we are observing in our experiment. Okay, so we have, I mean, we see, I mean, we have the interaction with the liquid, and I mean, the liquid, let's say, interacts with the terahertz pulse, and then we pass a pulse, an optical pulse, in with an angle, let's say, and we see that this pulse comes out with a rotated polarization. This is our observable. So this is perfectly in line with a Faraday rotation. This is what you will see. I mean, then the molecular Hall effect, I mean, came as a plausible, let's say, explanation of all this. And I mean, it would have been. I'm telling you now. I mean, this is not. It's definitive, but it's not definitive. What I want to say is that first, we tried several models of how to model it and how to understand it and what is happening there. And the most plausible explanation that happened is that if the molecular current is being introduced by our optical pulse, so it plays the role of the optical pulse, and then you have this interaction, let's say, with the terahertz field, the terahertz magnetic field of our terahertz pulse. I mean, basically, if this were true, and the deflection, let's say, from the Faraday rotation was coming by such an effect from the molecular Hall effect, this should have, I mean, the polarizability, let's say, squared should have this linear, let's say, dependence on the rotation that we see in our liquids. So, I mean, what I want to say, this was not a straightforward, let's say, connection. It's we are seeing the Faraday rotation, we are trying to explain it, we find a plausible explanation, we test this explanation by our experiments and our observables, and we see that they perfectly match. I don't know if this was convincing.
Is that fine by you? If you can follow up on the question, you can unmute yourself if you wish. Hello? I think should be okay then.
Okay.
I don't know. Please feel free to say if it's not. It's fine for me, the explanation. Okay.
Okay.
Very good. Are there further questions? Anyone else? Would anyone else like to ask anything? And on YouTube as well? I haven't seen any question on the live chat.
I mean, in YouTube, they can post comments, no? So if everyone comes up with a question, I mean,
No, we don't allow.
further question.
We don't.
You don't allow. Okay.
What we allow is live chat for the subscribers.
Okay. Okay.
Because unfortunately, we just don't have a large enough team to.
To moderate.
Yes, exactly. It's
Well,
just us. So
yeah, I mean, social media can be weird. So yeah, you need moderators there.
you always do. But I'm glad to say that people were in general very polite.
Yeah. Well,
But they should ask questions because I see they're quiet today. We have from time to time questions also from YouTube. And I don't see this is the case.
I
But
mean, it's not
huh?
I mean, if people are, oh, sorry, if people are happy, I am then happy. I mean,
Yes, I mean it was a very clear talk, and it is an interesting topic because you have these really strong fields and you can manipulate chemical bonds with those.
yeah. That's the case. I mean, basically, especially for the electric field, let's say interaction. I mean, I somehow told spit it out, let's say, during the presentation that I mean, at least the selling point for all this and what we envision, let's say, in the future, it's this coherent control of chemical reactions. I mean, if you can really manipulate liquid molecules, and with the liquids being basically the buffers of essentially every reaction that's happening, even you are talking about electrochemistry, photochemistry, you are talking about biological reactions and so on and so forth. If you can really manipulate bonds and alignment and anti-alignment states, and you can manipulate the energy transferred and so on and so forth, that gives you a handle on really coherently controlling chemical reactions, which is, I mean, the big picture, of course. We are far from this, but there is indication that most probably in some future we will be able to do.
That is amazing. How far are we from this? Because I know a lot has become reality, but still a long way to go.
I mean, it's very difficult to predict. I mean, to say it, to just give a time frame because, I mean, usually, many people are working to this. Many capable people are working to this, and usually it just takes a spark, let's say, to achieve it, and then everything goes and flows. So what I want to say is that I mean, usually these things are not planned. I mean, these things usually happen. So you have indications that they are building up, and at some point it happens. So it really depends. I mean, I cannot predict this. I mean, I don't know what to say. I hope soon.
You hope soon. It's
Yeah,
speculation, you speculate.
yeah.
You never know. So, thank you all for joining. We are going to finish our streaming and our recording. For those on YouTube, last chance to ask questions if you are a subscriber. So post your question on the chat, but I can see that people there are quiet today.
Okay.
Otherwise, all of you have a great weekend. If you are on Zoom, hang in there because you can ask our speaker some questions more privately if you are shy and don't want to be all over the internet. And for those on YouTube, have a great weekend. Have
Thank you
a
very much.
time. And thank you so much for joining. Thanks also, Vasileios, for this really interesting talk.